Yo, what is going on, everybody that is watching this video? Maybe in my class, maybe people who just watch this stuff for fun. I don't know. Welcome to another lesson of pre-algebra. We are starting a new chapter, chapter 11. This is 11, lesson 1. And we're going to be talking about square roots in irrational numbers. Square roots in irrational numbers. Now, the good news is you probably have some experience with square roots. We have talked about square roots in the past, and we're going to talk about irrational numbers, better define these things. All right, so before we can go ahead and talk about square roots, we need to kind of define what exactly is a square root. So in order to define a square root, we're going to focus on the keyword square. All right, and here I have three squares drawn out for you. They each have a different side length, where this has a side length of 1, this has a side length of 2, and this has a side length of 3. Now, if I try to find the area was base times height, or the side length squared. And since this is a square, if I multiply 1 times 1, I get 1 squared. 1 times 1 is the same thing as 1 squared, which is equal to 1. If I multiply and try to find the area of this square, because area is squarea, then we'll do this in a different color. Then 2 times 2 is the same thing as 2 squared, which is 4. All right, so the area for this shape is 4. All right, if I tried to find the area of this side, I would say 3 times 3 is the same thing as 3 squared, because whenever you multiply something by itself, that is a square. And 3 times 3 is the same thing as 9, so this has an area of 9. Now, looking at these different shapes, you can see that these are all squares, and they all have square areas. And whenever you multiply something by itself, that is what we call a square. So whenever you have whole numbers or integers multiplied by themselves, we call those perfect squares. And here are some examples of perfect squares, where if I tried to find the perfect square of 1 times 1, that is 1. 2 times 2, that is 4. 3 times 3, that is 9. And I'm not going to make you watch me write all these out. I'm just going to go ahead and pause the video. Then all these are going to magically appear. And boom, there you are. Now here I have a list of different perfect squares going from 1 squared all the way to 15 squared. And these numbers on the end, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225. These are all examples of perfect squares. Now, what we're going to be talking about today are square roots. So, if we're dealing with square roots, we can introduce the radical symbol. In this case, the radical symbol is going to look like this. All right. A lot of people call this a square root bar, but this is a radical symbol. And this indicates a square root in this case. If I asked you what is the square root of 4, you would say 2. Why? Because 2 times itself equals 4, and the radical symbol, a square root, is the inverse of squaring a number. All right, so if I asked you what is the square root of 1, you would say 1, because it is a number multiplied by itself. The square root of 4 is 2, the square root of 9 is 3, and so on. So here we have a list of the rest of them, where we can go ahead and figure out, well, what are all the square roots of perfect squares? And we can simplify them to its lowest term. So if you ever have the square root of a perfect square, like 1, 4, 9, 16, etc., then we can just take the square root, and we would get a whole number integer, the number times itself. So let's go ahead and take a look at example number 1, and these are going to be quite easy for a lot of people, because we're just going to be using our ideas of perfect squares. Like example, what is the square root of 64? Well, I do know that 8 times 8 fell on the floor, picked it up, made 64. So the square root of 64 is 8. That would be our answer, because we're looking for the number times itself that equals 64. This next one is a little different because it has a negative sign in front, and whenever you encounter a problem that has a negative sign in front, we're just going to keep it in front of our answer. I'll go more into depth on why that makes sense right after we finish this one. So what is the square root of 121? Well, 11 squared is the same thing as 121. So the square root of 121 is going to be 11. And our answer is going to be negative 11. Now, I said that we're supposed to keep the negative sign in front. Well, why is this the case? Well, this whole problem is the same thing as, well, if you ever have a negative sign in front, that's the same thing as negative 1 multiplied by that number. And if we simplify this step by step, we would figure out that this is the same thing as negative 1 times the square root of 121 is 11, and negative 1 times 11 is negative 11. So that is the long way to go about this problem. The short way to go about it is if you ever see a negative sign in front, we should keep it in front. All right? The negative sign is not inside the square root, and we are simplifying the square root by itself. So let's go ahead and try to simplify these square roots. The square root of 100 is the same thing as 10, because 10 squared is 100, and we're looking for the base. In this case, is 10. And it's positive, so our answer is positive. This one has a negative sign in front, so our answer is going to be negative, and the square root of 16 is 4. So our whole answer is negative 4. Now, not every problem that we will work in will deal with perfect squares every single time. Like in this example, they said you can use the formula d is equal to square root of 1.5h, and they give you a bunch of information. It says estimate the distance, so we're going to try to solve for d. We don't know what d is. But they do tell us the h value is 90 feet. So all we're going to do is evaluate. D is equal to the square root of 1.5 times 90. I know this is multiplication because a number next to a variable indicates multiplication. And if I use a calculator, 1.5 times 90 is the same thing as 135. Square root of 135. Now, if you remember, on our square root list, 135 is not a perfect square. 135 is somewhere between 121 and 144, where the square root of 121 is 11, and the square root of 144 is 12. So, square root of 135 is somewhere between it. So my question for you is the square root of 135 closer to 11, or is it closer to 12? Well, we can figure this out by using simple subtraction. If I subtract 135 minus 121, it's about 14 away. And if I subtract 144 minus 135, it's about 11 away. So it looks like this is closer to 12. So if we ever have to estimate the distance, and this problem asks you to estimate, we're just going to round to the nearest whole number. So let's look at standards check number 2, and they are asking us to estimate to the nearest integer. So that means they want a whole number. They do not want a decimal number. They want a whole number value. Now in this case, we want to say square root of 50. What two perfect squares is the square root of 50 between? Well, thinking about my perfect square list, 49 is a perfect square, all right, and 64 is the next perfect square, and square root of 49 is the same thing as 7, and the square root of 64 is the same thing as 8. So is 50 closer to 49 or is it closer to 64? Well, it's closer to 49. It is only 1 away to get to 50, where it would have to be 14 away to get to 64. So the nearest integer to the square root of 50 is 7. The last example that we need to talk about in this lesson is we need to go ahead and talk about the difference between rational numbers and irrational numbers. Rational, irrational. All right, so let's go ahead and break this down into two different categories. For rational numbers, the root word of rational is the word ratio. That means that rational numbers are any numbers that can be rewritten as a fraction. So common examples of rational numbers are numbers like 2 over 3. That's a fraction, so it's rational. What about the number like 5? Well, 5 is a rational number because you can rewrite that as a fraction as 5 over 1. So that's rational. What about a number like 0.2? Well, 0.2 is the same thing as 2/10 because this is in the tenths place value. So that means that this is the same thing as 2 over 10, which is the same thing as 1 over 5, which means it is rational. So we know that anything that is a fraction, anything that is a whole number, or anything that is a terminating, which means to stop, terminating decimal, is a rational number. Now let's go ahead and talk about irrational numbers. Irrational numbers are non-perfect square roots. Like an example of that would be the square root of 17. The square root of 16 is a perfect square, which means like if I had the square root of 16 and I reduce that to 4, 4 is a rational number because it's the same thing as 4 over 1. So that is fine. But if I have a number like the square root of 17, there's nothing much I can do with this. If you type this into a calculator, you'll get a decimal number that never stops, never repeats. You might be thinking, well, Mr. Lopez, if I type this into a calculator, eventually it does stop. It runs out of digits and I get some number. Well, the calculator only has so many spots of digits. So it actually never does stop. So square root of 17 is an irrational number. Also, non-repeating, non-terminating decimals. Those are irrational as well. For example, 0.321628. All right, this thing doesn't seem to stop, cannot stop, will not stop. And because there's no repeating decimal, there's nothing like, I guess an example of another rational decimal would be 0.3 repeated. This is perfectly fine as a rational number. But this guy is irrational because it never stops, never repeats. All right, so rational numbers versus irrational numbers. Let's go ahead and look at our last example of this lesson. All right, so example number 3 asks us to identify each number as either rational or irrational. All right, so I'm just going to use an R or an I. All right, just to clarify this. All right, example A says the square root of 18. Well, the square root of 18 is not a perfect square. It is actually, if I type this into a calculator, I would get something ridiculous like 4.242640687 blah 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 blah. So this is going to be considered irrational because it is not a square root of a perfect square. 432.8, for example B, is considered rational because this is a terminating decimal. It stops. If I had to write this as a fraction, I would get 432 8/10. And if I went around the world, I would actually get an improper fraction, so that's perfectly fine. Example C, 0.1212. It looks like it has a pattern. It looks like it's going to be 1, 2, 1, 2, 1, 2, 1, 2. So because it is repeating, that is considered to be rational. Now example D is 0.120. 1200, and you notice that these guys are not the same pattern. In the first set it has 1 0, and the second set it has 2 zeros, so this is going to be considered irrational. The last number is pi, 3.1415926 blah 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 blah. This is considered to be irrational because pi will always be an irrational number. Looking at the standards check, I can say that the square root of 2 is irrational because that's a non-perfect square. Negative square root of 81 is the same thing as negative 9, so that is considered to be rational. 0.53 is a terminating decimal, so that's rational. And the square root of 82 is a non-perfect square, so that's irrational. All right, that concludes this lesson. Good luck on your homework. I'm rooting for you guys. Bye.